So yeah, I believe a lot of people are here, and we'll start the session now. So I'll share my screen. Yeah. So I believe my screen is visible to everybody. Right. Just wait. So let's start with today's session. It's on biostatistics, data in the double helix, basically. So yeah, have you heard the term biostatistics anywhere, guys? Let's start with the basics. Okay. Yeah, yeah. Have you guys heard the term biostatistics anywhere before today? You guys just say in chat yes or no. It's fine. You don't need to unmute for this. Okay. So I believe not. Then yeah, it's fine. Let's just move on with this. So yeah. Today's session is in biostatistics and basically how statistics and math as a whole helps us in dealing with biological data. Right. Let's just get into the topic of today's session. So basically, how this is biostatistics is the application of statistical methods into biological sciences. Uh, so basically, this encompasses everything. Medicine, public health is given here, but other than this, there is something called scRNA and RNA analysis, bulk RNA analysis, and even phylogenetic analysis also comes under this. So let's start. Hmm. Now, basically, there are different type of variables in biological studies. Numerical continuous variables, basically like blood pressure, height, weight, temperature, and discrete, basically number of something. Like number of cells is a discrete variable. Like it says cell counts, hospital visits, and medicines that you're eating, medicines that you're taking. Those are all discrete variables. The nominal, basically, they are not related, like, in a certain order. They just have a set of values. Suppose it's A, B, and O. Now, I can give this like 1, 2, 1, 2, and 0. It won't make a difference for us. It won't be like 1 is greater than 2 and 2 is greater than 1 and 2. Right. So these nominal variables have something or some symbol assigned to them, basically. Then ordinal is basically stages, like first degree, second degree, third degree, that kind of thing. Like first stage cancer, second stage cancer, third stage, and fourth stage cancer. So these are the four types of variables that we usually deal with in biological data. Now, the fourth one, the ordinal one, is not of that much importance to us because it is more so related to research work and when you write the paper itself. The first three, though, you deal with when you're writing the code as well. So these three are more important to us right now. Last one, time to event, that is survival. Basically, there is something called Kaplan-Meier plot. It tells you what is the chance that a gene will be exhibited and how many days the person will survive, right, in presence of certain cancer, basically. Now, this is for HBB. HBB is hemoglobin. That is a gene that is usually expressed in all of us. It's not like it's a cancer's gene, though certain mutations in that gene can lead to cancer of different kinds. And this just shows like after the mutation has occurred, the probability of it mutating again goes to zero, and the probability of the person surviving the mutation also goes very low. So there is a very low chance that a person will survive the mutation in that particular gene. Okay, I'll get back to this at a later time. Let's just move on with this. So basically, we use different kind of statistics. As the name suggests, you guys are familiar with mean. That is sum of observation divided by number of observations. Median, that is the middle value in a sorted format when the data is sorted. Modal value, that is the most frequent value. Now, measures of variability, this is really important. So variance and standard deviation, sorry. Variance is just like the second moment, as you might know, of the second moment in the MGF is called variance, and the square root of that is called standard deviation, basically. Now, interquartile range is basically what's the distance between the quartile 3 and quartile 1 when you're calculating quartiles. I hope everybody is familiar with quartiles. It's a pretty basic topic that is taught in 11th and 12th classes as well. So this is the code to basically get the interquartile range, the variance, and the standard deviation, and the range. A range is basically the minimum and maximum values. So maximum minus minimum is the range, and summary is a summary statistic of that. Now, skewness and kurtosis. I believe there was a session a few days ago, lying with statistics. I went over this thing then too. I'm just giving everybody a refresher here. So skewness is the measure of asymmetry. How asymmetric your distribution is, like, is it right skewed, is it left skewed? That is defined by skewness. Kurtosis is the measure of tailedness. So basically, it tells us how sharp the curve is. How normal distribution, that is normal distributions have a kurtosis of 0 and a skewness of 0 as well. Skewness can exist in a normal distribution. Usually, though, when we are dealing in an ideal case, it is considered as 0. So moving forward, probability rules, I believe everybody is familiar with these two. P of A or B is P of A plus P of B minus P of A and B. This comes from inclusion exclusion principle that you have studied in 11th and 12th standard. Just okay. I can't add options here. Anyways, so Bayes theorem again. Bayesian statistics, I believe everybody is familiar with. And these are all actually just basic concepts. I added these in case anybody needs a refresher. Normal Gaussian distribution. This is the most common distribution that you encounter. The Z distribution, basically. And this is one of the most important distributions when you're dealing with any form of statistics because of something known as a CLT, central limit theorem. So basically, if you take a large enough sample size, the distribution will always tend to be normal, irrespective of the underlying distribution of any of those random variables that you have taken. The overall distribution will always tend to be normal. Now, following this, we have a binomial distribution. So binomial distribution occurs when each trial has two possibilities, either pass or fail, right? And we are doing the trial for a fixed number of times, basically. Suppose I'm flipping a coin 10 times. Now it can either result in a head or a tail. So that is what this is basically. And other important distributions are like T distribution. This is used for testing. Chi-square distribution is used for goodness of fit. F distribution is again used for regression testing and ANOVA. Exponential and log normal distributions are not that important for us here, as they have a very specific use case, which is more so observed in physics and like pure mathematics rather than here. So following this, we have hypothesis testing. Hypothesis testing basically follows a few steps, as you can see here. You propose something that is your null hypothesis. Basically, suppose null hypothesis is that which has no effect or no difference. So basically, you have two means, okay, and you're saying that these two mean values are the same. Suppose one mean value is 1 and one is 10. Now you want to say that mean 1 is equal to mean 2. That will be your hypothesis H naught or null hypothesis. Alternative hypothesis is what you want to show. That is That basically means, okay, 1 is not equal to 10. That is what you want to show. So we take 0.05 for research publications, right? And we take the test statistic. There is something known as a p-value, which is another statistic that we calculate based on the population data we have. And if it is less than alpha, we reject H naught. Otherwise, we accept H naught. Basically, what this means is, if suppose there is a alpha percent chance that H naught is true, right? There is an at least alpha percent chance that H naught is true. Now, in at least 5% of the cases, H naught will be true if alpha is 0.05. What this means for us is, it is not possible for us to statistically ignore and get the correct answer every time. And that is what this basically means. Now, uh, firstly, after this, we get errors. Now, everybody knows what an error is. It's a mistake or something that is like not correct, basically, error. Right. So there are two types of error: type 1 error and type 2 errors. Type 1 error is the false positive, and type 2 error is the false negative. Now, type 1 error is when the statement is false in is false in real life, but your testing or your statistics, they make it appear as if the statement is true. That is a false positive. And statement 2 is false negative. Basically, your statement is true, but they make it so that it appears false. That is what false negative means. Okay, so following this, we'll move forward. And there are different types of tests. Like going into the statistics of this is not necessary for today's session. I have added this. I'll share this. Like, if you guys want to go get more into detail about this part, you can ask me. Like, you can DM me or any of the board members. They'll send this file to you, and you can ask me any doubts you have over chat. Because this is a lot of like math. Because you'll need a base of this too. And as of most of you are second and first years, you guys are probably not familiar with this part yet. So if you guys are interested in this after the session, please feel free to contact me. I'll go into the biostatistic part soon enough. Then you can understand like what is exactly going on. This is just the introduction part as of now. So confidence intervals. Now confidence interval, like it says, it's a range of plausible values for our population. So basically, a 95% confidence interval or CI means if we repeat the same study like 1,000 times or a million times, 95% of the constructed intervals would contain the true parameter. Now, what this means? This means that the true parameter or the true value that we are looking for will lie in this confidence interval 95% of the time. Mm, okay, and this is the formula: CI for a mean, CI for a proportion. And yeah, then analysis of variance. This is a very important topic. It's a very simple topic, but it's a very descriptive, The formulas and everything is very simple for this, but the interpretation that comes after the formula is pretty tough. It's more so tricky than tough, and like it takes a bit of time to understand what is exactly happening here. So ANOVA is the first part, and then two-way ANOVA is the second thing. A regression analysis is basically when we have a bunch of features and we try to fit an equation which helps us to predict an outcome y. Like suppose you have x1, x2, x3, x4, and you make a linear equation out of this, which is simple linear regression, and you try to get a variable y that is the outcome, or the dependent variable based on the independent variable that is xi. That is your simple linear regression or SLR. So an example that I've given here is BMI and fasting glucose. So when you model fasting glucose as a function of BMI, you get a sum equation, okay, 55.2 plus 2.3 into BMI. Now, this is the expected glucose for a certain BMI, right? Now, glucose is Y, BMI is X, as you can see. BMI is independent, that it is not dependent on glucose, but it's not the other way around. Like glucose is dependent on BMI. Hence, we are taking glucose as the dependent variable. Now, for each 1 unit increase in BMI, fasting glucose is expected to increase 2.3 milligram per deciliter on an average. Huh. So R square is the metric that we use for like R square is the metric we usually use in regression and checking how good our regression is. Then there is multiple linear regression, like I said. Xi, there in simple linear regression there is only one variable x, but in multiple linear regression that can be n number of variables. But all the coefficient and all the powers are linear. So there is no such thing as a x1 squared kind of thing here in multiple linear regression. Logistic regression basically gives us a binary output that is between 0 and 1. And yeah, so you need to set a threshold for this. So if you take the threshold of 50, logistic regression returns a value between 0 and 1. And if your output is 0.51 and your threshold is zero point 0.5, in that case it will give the output yes, that is 1. And if it is less than zero point 0.5 or whatever threshold, it will give the output 0, that is no. So an example is given here again: predictors, family age, BMI, age, family history. Then we have calculated the formula using the formula here, and the odds of increasing diabetes are by 20%. So this is the coding part. Yeah, and all biology related coding is usually done in R. Now this like is a bit of a unusual thing for most CS people, as we don't really use R that much on a daily basis. We are more well versed in Python, C, C++, and other languages. R is used because all bio-related packages, there is a CRAN package basically. It's a bioconductor package. So it has a bunch of really important and really useful tools which statisticians and like bioinformatics people use, scientists use to calculate various things from the biological data that they have been given. Then there are non-parametric tests. So basically, parametric tests that we have that we studied earlier, they make a certain assumption about what kind of distribution the data has. But non-parametric tests have no such assumptions, or even if they have very small assumptions. Like there are a lot of different type of distributions, and suppose one sample t-test we have been given here, and non-parametric equivalent is the Wilcoxon single rank test. This is one of the most common tests, Wilcoxon single rank and Wilcoxon paired. These two tests are the most common type of tests that you'll encounter. Spearman correlation and Friedman tests are also pretty common, but Wilcoxon is the most common test you'll encounter. Now, non-normal data is basically data that does not follow a normal distribution. It can be any other distribution, just not a normal one. You can use this test then. And like we discussed earlier, the results that you get are just hypothesis testing. Either you prove H naught or you disprove it. That is rejected. And yeah, moving forward, survival analysis. So it's basically survival till what? If a person X has some disease, till what time can they be survived can they survive on an average, given something about them, basically their relapse chances and recovery percentage and how well they're responding to drugs and everything. So that is what we do. Now, like I said here, Kaplan-Meier estimator is here. It's a non-parametric method to estimate survival function from observed data. So basically in USA there is this thing called NHAI, National Health Institute. they store the data of most of the patients that consent to this, and they like train models on it, and those models tell us and or generate estimation statistics for other people that doctors use as a reference. uh, so basically, like I said here at this part, this is a Kaplan Meier plot, and this is the code to generate it. Just a second, guys. Sorry, guys, for that. Yeah. So sample size and statistical power, it is usually considered a good thing to keep a larger sample size, and the thing that limits us when comparing to sample size on biological data is the sheer number and our machine's capabilities. Now, you can have a very powerful machine, but I'm pretty sure if you go have a decent topic and research has already been done there to a significant amount, there will be a lot of data and it will not be processed able. It will be not sorry. Yeah, you will not be able to process the entire data that is available, even if you can merge it into one data set. It is just that vast. And yeah, so multiple testing and effect sizes. This is again that just into a deeper part, and study design epidemiology. So yeah, basically choice of design, study design that determines what causal inferences can be made. So basically, there are different tests and studies that we design when studying about sorry, when studying about diseases or cancer or something else. So when we do case studies, whether it is retrospective or prospective, single point, it is variable time. There are we observe it in different point in time and everything. Is it randomized? What are the strengths and limitations? Now, a lot of medical studies, as we know, have ethical constraints, right? So everything that is done here in biological data and biological data science and all is usually is I mean not usually is always done with the consent of the patient and the doctors. And yeah, so then again, correlation analysis basically gives us a measure of how two variables are limited. We'll do a short like study on this. Following this, I have a few things prepared for you guys. We'll look into it, and then yeah. So correlation are of different types. A Pearson correlation is the classic definition of correlation that you will see most of the time. But when things are ranked, you'll see the Spearman rank coefficient. It is a non-parametric alternative to Spearman's to Pearson correlation. Pearson correlation assumes a continuous and normally distributed data, while there is no such assumption in Spearman's coefficient. And moving forward, this is just a guide for what kind of a test we'll use. Um, and these are the formulas of basic, like, sorry, these are the formula of basic statistics that we'll be using when studying anything actually, not just biology, anything. So mean, variance, standard error, score, z-score, t-statistic, ci. So 95% ci is basically 95% confidence interval, like I said. Relative risk, odds, and sensitivity. There are some others, but yeah. Coming forward to the actual biological part. Now, bulk RNA sequencing is done when you have a very large tissue that is suffering from some disease, let's say some sort of cancer. Okay, and okay, a lot of examples that I take today will be of cancer because that is one of the most studied things, and that has one of the highest number of research publications. So it's just easier for a to introduce someone to this field to just take an example of a popular cancer. So yeah. So bulk RNA sequencing. Basically, what we do is we extract the cells that are present in a tissue and we process them. Then we extract the transcripts from the cell in the bulk form. So basically, we don't go to each cell and get the transcript. We just rupture the cell walls of the entire tissue sample that we have taken, and we just average out the transcripts and get the counts that way. Now, this is a very old technique, but this is the cheapest technique available to us, and this is one of the most like technique. This is one of the techniques used to basically as a ground truth for your research. When you're doing your research, this technique is the ground truth. Like, you need to first prove it via this study. Okay, this thing that I'm proposing, it actually exists in the bulk form, not just at a cellular level or subcellular level. So this is the most basic analysis that anybody will do. It uses the DE-SEQ2, and ggplot is just for plotting. So DNA sequencing 2 is a library that we have using. It's a BioC manager or CRAN package. Like I said, so BioC manager is another bioconductor packages that you can install in R. Now there are certain steps. So you load the matrices, like you're seeing here. Then row names of one. So what this means is the first column that you have, that will become the row names. Now column data, you just split it into two parts: control, and like treated. So actually, this data is in a form of like has a lot of metadata. So we are just filtering that here, so that R can easily read it. There is a library called Soiret which can do this for you automatically, but this is the like basic approach that is usually used for people who are learning. When you have learned this part, you can go into like Soiret and other more advanced versions of the software, or like more advanced libraries. So filtering, we remove the low count genes. Now the thing is, when you're doing this, there are some genes that might appear due to interaction between transcripts, and those genes don't actually exist. They are just there because there was some chemical reaction that took place, and yeah, they just appeared out of nowhere. As it is a real life scenario, this kind of stuff happens. So we just remove all the genes whose count is greater than we remove all genes whose count is less than 10. Basically what this means is all genes with a count of less than 10 will be filtered. That is, we are only keeping the genes with a count of greater than equal to 10 here. Now we start the pipeline here: log to fold chain, shrinkage, and visualization. Now, log to fold chain is basically used when you have a microarray data set and you need to check for the significantly enriched genes in the data set. I have another report here. After this, I'll get into that. First, let's just go through the code now. Now, significant DEGs. DEGs are differentially expressed genes. Differentially expressed as in, what differentially expressed means is, basically, suppose in your body, now your tongue, your eyes, and even your hair, right, and your feet, everything has the same DNA. But how are they different? How does a cell know when it has to become a kidney, when it has to become a liver, when it has to become a tongue or eye or an eye? How does a cell know that? And what is different between these cells? Because it's not like you can, if somebody loses their eye, they cannot just take the skin and put it in the eye and it will grow a new eye. It's not like that. So what is it exactly? Is this differential expression? So differential expression of genes is basically, it's a concept that different genes are expressed in different amounts in different cells or different tissues. That is the basic concept behind this. Significant DEGs are those that have a log to fold change greater than 1. 1 is the basic bare minimum threshold that we take. Usually, when studying new DEGs or new differentially expressed genes, we take a threshold of 1.5 or 2. One is the bare minimum threshold that we take. If you're not getting anything, one is okay, you can take one, you'll definitely get something. But if you really want to get into newer things that haven't been studied yet, just make this a bit higher, the cutoff a bit higher. We use a volcano plot along with this and heat map top 50 DEGs. I'll get into it this near the end. Oh, and PCA for sample quality control. Do you guys know what PCA is? Have you guys heard the term PCA? No. Guys, anybody? Principal component analysis. Have you heard the term before? Okay, I believe you haven't heard it. So PCA is a method of dimensionality reduction. Suppose you, in usual, like in real life scenarios, you have a very large data set. Like I have a data set installed here. I'll show you one of them. Data sets. Let's just get into this one. First data set. Okay. Let's hope it loads because yeah, it's load. It has loaded. Great. So as you can see, we have so many genes here. Like this is just the first row. It's like breaking because there are just so many genes it can't fit in a single row. And as you can see, it's a very large column. It's a very large file that you have seen here. And it has thousands of rows. And amongst these thousands of rows, you need to filter out which genes are important and like which genes are actually you're going to use. So how do we do that? And that is the main question that we use math for, or we use statistics for. Now I have done a study on this as my subject. So basically, we used high variability across, like conservation of variability basically as a concept. So what I mean is, suppose you have a certain gene that is exhibited. Just a second. Yeah. So imagine you have a certain gene. This is the coding part. I'll just get to the graphs. Yeah. Not this one. I think this one works. Triangles. Yeah, this part. So imagine you have a certain set of genes that is highly variable amongst different type of cells. Uh, you have tissues, obviously you will have multiple cells, right? So this is how tissues are visualized here usually. Now tissues, this is from a neuroblastoma. So neuroblastoma is a cancer that can occur anywhere in your nervous system. For a person's nervous system, it is mostly a cancer that appears in children of age like 2 to 3 years. It's very rare for it to occur in older people and older kids. So it's mostly a pediatric cancer that is very deadly actually. Hmm. So yeah, imagine these are the not imagine, like see, these are the different cells that we have in neuroblastoma: chromaffin, sympathoblast, neuroblast, stromal cells, matrix-producing CFs, and ganglion cells. Now, the thing is, these are all present in the same tissue, but they have a different D expressions. They have different gene expressions. That is, they have different DEGs. And actually, if you have a certain number of DEGs, like 4 or 5 DEGs with the expression levels, you can use it to identify which cell is it and of which tissue does it belong to. You can actually use it to identify that, right? So suppose we have the biomarkers here. Now you see there is this sort of a line going diagonally here, right? These are the DEGs that respond to the corresponding class. Now what is the corresponding class? There are different classes here, right? As you can see, there are 1 2 3 4 5 6 classes here. Now actually there exists sub differentiation between these classes too. Those are like, there are different type of neuroblasts, there are different type of stromal cells, and some cells are in different stages of their lives. So they have different expressions throughout their life. And since cancer cells keep on dividing, there are certain genes that promote cell division that are often seen to be enriched in that case. So suppose you see this diagonal here, right? The diagonal is thicker compared to others. So the diagonals are the marker genes, and marker. What does a marker gene mean? A marker gene is basically, okay, you can use this gene to identify this type of cell. That is what a marker gene is. Suppose you have some gene like UNG and you have HPDL, these two first two genes, and you are asked which what kind of a cell is this. You can easily identify because in others it is not as highly expressed. As you can see, the color is darker here compared to the others. That is why you can say, okay, it's type 0 cell or whatever the type 0 cell here the name is. So this is basically how you identify a cluster with a marker. So suppose you have this gene ADM, and DAB1. Now you have been given these two genes, and you're asked what kind of a cell is it? It's cell type 10 because it's not exhibited in any other gene. So it is cell type 10 that exhibits or has the marker as this particular gene. That is what we get from this. Now this is again another very interesting graph actually. So suppose you remember PCA I told you, right? Principal component analysis. After that, after PCA, we reduce the number from 10,000 or like 20,000 genes to 50 or 100 genes. Okay, whatever the computer can calculate, we reduce it to that many. It's usually 50. Now those 50 genes that we got, we need to reduce it to 2 dimensions because still humans can't see beyond 3 dimensions, and we really don't want to complicate the data. So we make sure, like, make it in a way that we can see the data that is thousands of dimensions large in 2 dimension. That is again another form of dimensional reduction called UMAP. This uses manifolds. Manifolds is a very like interesting topic in mathematics, and we use those manifolds to reduce the data structure, data size here. So the thing is, just open it again. Where did that go? Yeah. So you remember this large file, right? That opened. Yeah, this large file. This very very large file. Instead of this thing, it'll just be the first two columns. I mean, not these two genes, but it'll just be reduced to two columns. That's it. UMAP one and UMAP two. That is it, and that is how we actually deal with the data. So basically, this shows the uh, the exhibition of different genes in different data, like different parts of the data, right? So suppose this COL31A gene. Now, as you can see, it's exhibited in the central part. What was the central part again? If you remember, it's neuroblast. So this particular gene is exhibited only in the neuroblast. But as you can see, UNG, this gene is exhibited almost everywhere, but it's like specially exhibited in the bottom right part, bottom left part. What was bottom left? Stromal cells. So you can say stromal cells have a higher exhibition of UNG based on the graph, and there are a lot of like other graphs as well. So you can make these graphs very easily using R. And suppose this thing, GAS 2L3. Now you can see it's exhibited on the right side of the distribution. What is on the right side? Sympathoblast. So you can say that GAS12 is exhibited majorly in sympathoblasts, right? Then cell type annotations. The thing is, in real life, the cells don't have numbers now. Cell types are given names, actual names. So here also we give the names. Now, how do you determine these names? There are softwares that exist that help you determine what the cell type names based on the marker genes that you have. And if you don't want to use the software, you can do a literature survey as well. So you can search the name in PubMed or any other like Web of Science or any other medical journal that you like. or a medical website that you like, and then you can read through the papers, and they will have named the cells there. You can use that, and you can use text mining as well, to tell the, okay, this is a mesenchymal stromal cell, or this is a mitotic sympathoblast. That is what is basically happening there. Uh, okay, so as you can see, there's like matrix predicting CF, parasite like stromal cells. There are different type of stromal cells, like I said before. There are different ganglion cells. So ganglion cells are in different stages of their life. Immature is like they are newly born. Mature is like they are ready to reproduce and like split into two, basically. Hmm. So this is DNA damage tolerant neuroblast. So there, if like these are kind of cells, they are at some point they might have been exposed to some kind of radiation or something that might have damaged the DNA, but they were able to recover from that, and it's like very hard to damage the DNA in these cells, or they're like in a quasi immunity to cancer, like semi immune to cancer in a way. Now this is the volcano plot that I said talked about earlier. The top genes that are marked here, that are labeled, are your HVGs, highly variable genes. So these are the genes that have a high variability. Now, what our proposition was while writing those research paper was key. Okay, there are certain genes that are highly variable in one data set, but what if we find a set of genes that are consistently DEGs or highly variable in other data sets as well? Hmm. So that is what our main proposition was, and we call them consistently variable genes, as you can see here. So what is the purpose behind a consistently variable gene? So these are the like basically we took about 100 different cancer patients, and we took their samples, and we made the plots for them. We studied them, and we got certain outputs. So firstly, consistent variability. What exactly does that mean? Consistent variability means ki the way, uh, you know that your variability will be consistent. That is, whenever this gene exhibited, it will always be variable in different type of cells. And if it is different and variable in different type of cells and static in the same type of cells, you can say, okay, that is a marker gene. Thing is, this uses a very simple mathematics, just variance and a few other stats and tests. But when you go into UMAP and PCA and all, they use a very like what can I say, a very high form of mathematics, which is firstly not easy for most people to understand, as most people who study this are from a biology background. And secondly, people who do understand it, it's very hard to tell when you have made a mistake because the math is just that complicated. So we introduced this as a alternative method, and I'll just make get to this. So firstly, we check for the variability of the gene. How variable is the gene? So as I said, you can just take the log to f here. Whatever the value you get, if it's greater than one, it's variable. If it's less than one, it's not variable. That is it. And following that, once you have the list of variabilities, now you need to decide on the consensus. Okay, how, like, out of the 100 data sets that you have, how many data sets do you want this gene to be variable? So we took, like, these terms we made on our own, because there was really no precedent on this. So ultra, high, moderate, and low. Ultra consensus was like, okay, this gene is variable in every single data set. High was like 70% data set, moderate 50%, and low 25%. And this was the code again. This was in Python, like, because I didn't use any libraries as such at that point. This was more so a new application, novel application from our side. I coded it in Python. Hmm. So as you can see, we have different windows for persistence. Uh, Now, consistent variability and persistence are like interchangeable stuff, and interchangeable terms in this paper. Okay, and As you can see, gene X is variable in 60% of sample. It gives a persistence score of zero point 0.6. So a persistence score of X means that that particular gene is variable in X% of data sets, basically. And for the biological interpretation of persistence patterns, so high persistence is universal heterogeneity. What does universal heterogeneity means is, okay, this thing varies a lot. So among different kind of cells, and it has varied for different people and different patients, and like even within the same tumor in different region, it has varied a lot. So there might be some biological significance to this. Now we cannot prove that without doing a physical experiment, but it is usually the case that there is an exhibition of this kind of a thing. Hmm. Moderate persistence. Now this is just a simple, like, probability thing. Like, okay, it's a very high persistence, so there is a high chance of biological significance. It's a low persistence, so there is a lower chance of biological significance. And very low is like, okay, there is a negligible chance, but we can't just rule it out without testing it out anyways. But our priority should go from top to bottom, like high, moderate, low, and very low. It should go like that. Now, integration with correlation networks, basically. Uh, so there is this thing called a clique in a graph. Now, a clique is basically a set of variables. I mean, a set of nodes in a graph that form a complete graph. Uh, so basically, we have the triangle clique here, as you can see. Now, a lot of the nodes form there are 40,000 triangles in this particular data set. But there are datasets here as well with very low triangles. Now, why is this? This is because at that point in time, used a very high cutoff, and only these variables were there, which actually showed promising results. And I'll get into this in a bit. Again, nodes, edges, density, communities, clustering, and modularity. So network robustness goes down as we increase the number of fractions removed. So network robustness, you don't need to get into this term. Just imagine, you have a disconnected network. Now how big is the largest part of that network? Just imagine it like that. And if you start removing nodes, like you remove 20%, 30%, 40%, 50%, 60%, what is the relative size to the other nodes of the largest largest community, basically? And these are the different metrics that we got for different genes: degree, betweenness, closeness, eigenvector. Following this, this is how basically the networks look. Okay, how the networks are. As you can see, there are different networks here. Advantage over traditional. So basically, from what our study we were able to find is, n% persistence up to a certain degree, like 50 to 60%, gives the same result as HVGs, and it's a lot faster actually compared to HVGs. How HVGs are normally done, it's a lot faster. So you can save a lot of time doing this. Based on this, we were able to actually find a few new relations between genes that were absent from existing databases. Now, clinical applications are basically, see, when you have two gene interactions, suppose this one is causing a certain type of cancer, and this one you can target, and as these two are closely linked. Okay, when this one goes down, this one will also go down, and when this one goes up, this one also go up. Or it could be like the opposite one, inverse too, either way. So you can target this in a certain manner, such that you can regulate this with the help of gene 2. Now it's like possible in either way too. There are really big networks of these things called transcription factors, and like there are networks of this, like this. So suppose you are targeting this one particular gene here in hopes of getting output here, right? You want to target this gene, but you don't have a drug. There hasn't been a drug discovered yet to target this gene. but you have one for this. So you need to find a path between these two genes and how it will be target. Suppose this one. So this is like one, two, three, four, and five. This is the path. There's a simple path between these two nodes, as you can see. And yeah, so network topology, like I said, bottlenecks and everything we have discussed it here. This was the community graph actually. So communities are basically, there is a Leuvian community detection algorithm in Network X. We use that here, and it was able to detect the closely linked communities. So there is a factor called betweenness, closeness, and like degree and density of nodes. And based on all those factors, the Leuvian algorithm, it calculates the community. Basically, it's a clustering type of algorithm, and the color nodes of the same colors are in the same cluster. Hmm. So that is how this usually goes. And this is the distribution of HVG frequencies. So basically, high consensus, there were like nine data. Sorry. So there were a lot of genes present in only one dataset, then a bit lesser in two. Then as you increase the number of datasets, your gene keeps falling low and low and low. Hmm. So then I guess as you can see, the least number of genes are in 28 datasets. And we have the list here actually. I'll just show you now. High correlation pair and high correlation like this one. So as you can see, there were I think 29 pairs of genes that were present in 75% of the datasets. That is, 75 out of 100 datasets has had these pair of genes exhibited together with a high correlation, like zero point 0.8, zero point 0.9 level correlation. And yeah, let's just close. And um, and another part that we used was explainable AI. So explainable AI is basically an unsupervised learning algorithm. It's not exactly AI per se, but it's more so it helps you to get an insight on how your model is actually working. So suppose you have a random forest classifier or an XGBoost model. Now, how that model is changing its weights and biases and how it's actually adapting to the data. How much does the feature affect the result? That and all, if you want to know, you need to use something known as XA or explainable AI. There are a lot of ways to do this. The most common is Shapley and Lime. So Sharp is the one that we went for here. We have the Sharp score somewhere. I don't think I've added this to the report, but yeah. So Sharp we have used here, and I'll just show you. This is the violin plot. I hope you guys are familiar with violin plots. They're like the fundamental plots that you use, and box plots, cluster maps are there. So cluster map, this is a dendrogram actually. It's like a hierarchical clustering algorithm applied on the genes based on their correlations. And this is the correlation network of a gene with a like high interval like point greater than 0.05. And yeah. Now this is the future opportunity part, and like, this is just the research work. Then this is the code, and now so guys, do you have any questions? Like, were you able to understand what was going on? Like what I taught you guys today? Hello, guys, anybody? No one. Uh, yeah. If you guys want to ask or like you want the session notes or anything, just DM one of the board members or DM me. You have my number. Otherwise, yeah. No, okay. Aniruddha, Saksham, you guys, if you have the sheet, you can circle it. Like, I'm done with the session. Guys, make sure you don't leave before filling the form. So once you guys are done with like filling the form, you can leave the meet. Yeah. Thank you. Yeah. Thank you for attending the session.